Welcome. Thanks for continuing to watch our series of videos from the EANTC multi-vendor MPLS and SDN interoperability event. Now, regarding the name, it's called MPLS and SDN interop event, but for a long time we have covered other technologies that are very important as well for the telecom deployment, specifically for mobile networks of the future. So since 2012, if I remember correctly, we've been covering clocking, clock synchronization, precision timing protocol, synchronous Ethernet in the past times, and the requirements for the synchronization have always increased. Now, when we tested synchronization for LTE a couple years back, we already had thought that we had reached a huge gain and the limits of what can be done over Ethernet and IP technologies. But with 5G, the challenges are ever increasing. So we have expanded the testing and we've tightened the screws this year again for the testing of so-called Class C telecom boundary clocks according to the G8275 telecom profiles. So all of these details are much better explained by Mark Black from Microchip. So over to you, Mark.
Hi there, my name is Mark Black with Microchip. I'm here at the EANTC Interop here for 2020, and we are going to present a demonstration in the clocking division. Today we'll be demonstrating a phase time, full timing support, boundary clock Class C test. The importance of this test is to demonstrate the ability of maintaining the 30 nanosecond accuracy needed for today's 5G networks. And this is pertaining to the ITU G8273.2 standards. The purpose of this test is to verify that the slave clock or slave clocks in this particular instance can maintain the required synchronization quality when using the G.8275 profile with the full timing support with SyncE. So in this test, we verify that the chain of boundary clocks, class CD, in a network is providing the full timing support and maintaining the phase accuracy requirements. In this test, we're going to use the Calnex measuring device, and this is measuring the phase accuracy right from the GMA and the GMB right through to the slave clock. With this test, I'm going to just walk through it here. We have obviously 4 or 5 different vendors here. We have a Clock A Grandmaster, Clock B Grandmaster, and the phase accuracy will travel through the boundary clock path to the end slave clock device, which is measured with the Calnex. So in the first step, we'll disconnect the GPS from the Grandmaster Clock A. The GMA with the higher priority will actually first take the measurements through the boundary clocks to the slave, measuring the minimum 30 nanosecond accuracy. So here we see through the GMA, we have, I believe, 4 different vendors, each having their own slave clock. So the first one being Ciena, and we can see down here in the bottom left-hand corner the green 30 nanosecond accuracy pass message. We can then move on to the next one, Huawei. It is as well within the boundaries. Microchip, again, showing a 30 nanosecond pass. And the 4th slave clock, ECI, as well, showing a 30 nanosecond accuracy. So with that, we will now move to the second step, which is disconnecting the antenna from the GMA, which will cause us to fail over to GMB. And after 300 nanoseconds, we will again measure the accuracy, the phase accuracy of this boundary clock path and demonstrate that the accuracy is maintained throughout the test with each slave clock.